So we are going to look at characterization of connectedness in a topological space. So in some books, they will interpret this theorem as a definition of connectedness. So the theorem or the definition says that a topological space X is connected. A topological space X is connected if and only if the only two clopen sets of X are X itself and the empty set. So it's like saying that a space will be connected if the only simultaneously open and close, if the only simultaneously open and closed sets are X and the empty set itself. So how can we prove this statement? So we are going to prove that it's an if and only if statement. So the forward direction, suppose that X is connected. Suppose that X is connected. Then we know that in a topological space, since X is a topological space, we know that in a topological space, this X is a topological space, then X is X and the empty set are open sets. In a topological space, the set and the empty set are open sets. And similarly, they are also closed sets. Also, so we know that in a topological space, the set and the empty sets are open. So they are also closed because you try to compute their complements. We say that a set is closed if its complement is open. Also, the complement of X, the complement of X, the complement of X is X minus X, which is equal to an empty set. And an empty set is an open set. So the complement of X is actually an empty set, which is an open set, implying that X is closed. X is closed. Similarly, the complement of the empty set, the complement of the empty set, which is X minus the empty set, is equal to X, and X we know that it's an open set. So the complement of the empty set is an open set, implying that the empty set is closed. So this implies that X and the empty set are clopen in X. Conversely, suppose that we are going to prove the converse direction. Now we are going to do what? Conversely, suppose that the only two clopen sets of X are X and the empty set. Suppose that the only two clopen sets of X are X and empty set, then we are going to assume by contradiction, suppose that X is not connected. Suppose that X is not connected. What does that imply? So this implies that X has a separation. This implies that there exists open sets A and B in X, A and B non-empty, A and B non-empty, A A and B distinct, and they are disjoint, and X is actually equal to A union B. X is actually equal to the union of distinct disjoint sets. In simple terms, X has a separation. So there exists open sets A and B in X such that X is equal to this. So observe that observe that A and B are open sets. Open sets which are disjoint. What does that imply? Open sets which are disjoint. So open sets which are disjoint, we are going to compute their complements. So they are observed that A and B are open sets which are disjoint. So we are having our A and our B here. This is A, B. They are disjoint. So try to compute the complement of A. Elements in X but not in A. Elements in X but not in A. That is the complement of A. Then A complement which is X minus A is equal to B. Is equal to, I have to be somehow careful. Yeah, A complement which is X minus A is equal to B. This is an open set. So the complement of what? The complement of A is actually an open set. What does that imply if the complement of a set is open? So by definition, a set is closed if and only if its complement is open. A set is closed if and only if its complement is open. So if the complement is open, then the set is closed. So the complement of A is an open set, implying that A is closed. So this implies that A is clopen. Is closed and open. Similarly, complement of B, which is X minus B, is equal to A, an open set, implying that B is closed. B is closed. So this implies that B is clopen, closed and open. So this is a contradiction to our original assumption that the only two clopen sets of X are X and the empty set. So this implies that A and B. This implies that A and B are also clopen, contradicting our original assumption that actually X and the empty set are the only clopen sets. This is a contradiction of our original assumption, implying that our original assumption was actually wrong, implying that X is connected.